Assalamualaikum students and fellow physics enthusiasts. One of the applications of Faraday's and Lenz's law of electromagnetic induction is the production of an induced EMF and current through a coil of wire. How is this made possible? To find out, just hang on till the end of this video. Watch and learn. The question is, a circular coil with 455 turns of wire has radius 5.00 centimeters and resistance 14.5 ohms. The area vector of the coil points in the positive C direction. The coil is in a region of uniform magnetic field that points 20.0 degrees from the positive Z direction. The magnitude of the field is initially 0.0600 Tesla and decreases at the rate of negative 3.00 raised to the negative 3 power Tesla per second. Find the magnitude of letter A, the induced EMF, and letter B, the induced current in the coil while the field is changing. A simple experiment can be done to demonstrate how a change in flux or magnetic flux can induce an EMF and current in the coil as shown in figure 1. A circular coil with 455 turns of wire also has a radius 5.00 centimeters and resistance 14.5 ohms. If we move the bar magnet into the coil, with its north pole facing the coil, and then withdraw it from the coil repeatedly, we see that the needle of the galvanometer connected to the coil to deflect back and forth. And we infer that there is current induced in the coil, and that this current seems to depend on how fast we move the magnet into and away from the coil. In figure 2, we can imagine the cross-sectional area of one of the loops of the coil such that its axis is perpendicular to the xy plane. Thus, the area vector capital A is directed into the reader, or that is, into the positive z axis. Notice the dot symbol for the area vector capital A, all right, suggests that it is indeed into the reader or into the positive z axis. Also, the z component of the induced magnetic field capital B sub z is also in the same direction as the area vector, all right, which is towards the reader or into the positive z axis as well. The angle theta that is formed between vector capital B and vector capital A is given, all right? Angle theta equals 20.0 degrees from the positive z-axis. The rate of change of the magnetic field is also given. We denote this rate of change of the magnetic field as delta capital B over delta T. It is equal to negative 3.00 times 10 to the negative 3 Tesla per second. And the magnitude of the initial magnetic field, capital B naught, is equal to 0.0600 Tesla. And our target variables are in part A, the magnitude of the induced EMF in the coil denoted by epsilon. And in part B, the magnitude of the induced current in the coil while the field is changing. So this current, capital I, is just equal to the amount of the induced EMF epsilon divided by the given resistance big R of the coil. Before going into the computations of our um, main questions, we first compute for the magnitude of the area vector capital A, or that is the sectional area of the coil. Of course, that is just equal to the product of the value of pi times the square of the given radius, or 3.14 multiplied by the square of the given radius, 5.00, raised to the negative 2 meters. So we get the magnitude of the area vector capital A, or the cross-sectional area of the coil, equal to 7.85 times 10 to the negative 3 meters squared. Likewise, we also determine the rate of change of the magnetic flux, okay, denoted here by delta P sub B over T, right? But in terms of the area vector, delta phi sub B over T can also be expressed as delta B over T, okay? That will be multiplied using the dot multiplication or the scalar multiplication. So delta B over T is dot multiplied by the area vector capital A, right? And since we are just after the Z component of the magnetic field, or capital B sub Z, all right, equal to capital B cosine theta, therefore, what we are computing here, right, is the Z component, right, of the magnetic flux. So substituting, we get negative 3.00 raised to the negative 3 power Tesla per second, right? That is the what we call change of the magnetic field, all right? And then that will be multiplied using scalar multiplication by the area vector, all right, that we have just determined here, 7.85 times 10 to the negative 3 meter squared, and cosine of the angle theta, 20.0 degrees. So when you do our math, we find this z component of the magnetic flux, right? Or the rate, the change in the magnetic flux, equal to negative 2.21, okay, times 10 to the negative 5 Weber per second. And this unit, Weber per second, is just the same as the unit volt, right? The meaning of the negative sign in our answer, right, is the fact that this change of or the rate of change of the magnetic flux, right, is in fact decreasing, right, which agrees with um, Lenz's law. All right, we go back to figure 1, where we have this setup of a bar magnet that is being moved back and forth towards and away from the coil, right? This time, we consider only the action of moving the bar magnet away from the coil, which is also connected to a current measuring device or a galvanometer. All right. So this time we call it figure 3, right? The original figure, figure 1, illustrates the action of moving the bar magnet towards the coil and away from the coil. But this time we only consider the part where uh, the action is only during the moving the bar magnet away from the coil. So according to Faraday, withdrawing the magnet away from the coil induces a magnetic field in the coil, right? The decreasing magnetic field, capital B, induces the EMF epsilon and also the current, capital I, in the coil. How does this happen? All right. So um, the fact that the amount of the magnetic flux that is intercepted, all right, or induced in the coil is in fact changing in or decreasing. So a decreasing amount of the magnetic flux that is being induced is the condition uh, for the coil to also induce what we call an electromotive force or EMF that was explained earlier. All right. And if the rate of change in the magnetic flux is high enough, then we say that the amount of induced EMF will also be greater. All right. So, in addition to what Faraday is telling us, we can also mention here Lenz's law. All right. Since the bar magnet, which is the source of the external magnetic field, all right, is moved away, okay, the coil becomes like a what we call electromagnet, whose polarity is such that uh, the left end, okay, facing the bar magnet, becomes south pole, and the right end, of course, is the north pole. So the direction, all right, of the induced magnetic field or magnetic flux is directed from south to north. We're talking about the direction of the magnetic field inside the coil, that is. And this arrow, the blue arrow, represents the magnetic field that is induced in the coil, or when multiplied by the area, all right, by the area vector of the coil, then that also can represent what we call the change in the magnetic flux, right? So how does Lenz law come in to this picture? All right. According to Lenz law, all right, um, if you're going to move the magnet away, all right, the coil will sort of prevent, okay, the action of moving the magnetic or the bar magnet away. So that is the reason why uh, the end of the coil that is facing the bar magnet becomes a south pole. All right, between a south pole of the coil and the north pole, right? We have what we call a an attractive force. That's magnetic force. Only a south pole, okay, can exert an attractive force on the north pole of the bar magnet. Okay, so in order to uh, materialize the production of energy in the coil, okay, the bar magnet, okay, has to overcome such attractive force coming from the coil. And that is also where the conservation of energy comes in, right? To successfully have an induced EMF, all right, in the coil, or we call it voltage, okay, uh, an outside agent, okay, has to pursue in moving the bar magnet away. All right? The faster you move the bar magnet away, the greater would be the induced EMF. All right. Work has to be done. In other words, okay, work has to be done from an outside agent, okay, to move the bar magnet away because there is a force of attraction preventing such an action. So if you're able to overcome, okay, that force of attraction, then you will be doing work. All right, you will be doing work for moving the bar magnet away, and that is where the production of energy in the form of electrical energy happens, okay, in the coil circuit. That is where the law of conservation of energy comes in. All right. Now, going back to uh, the production of the induced EMF, that happens because uh, the rate of change of the magnetic flux is also changing, right? In fact, it is decreasing, as mentioned earlier. A decreasing magnetic flux within the coil results to, all right, the induced EMF. Remember, the induced EMF is just equal to the amount of the rate of change of the magnetic flux. When you say magnetic flux, we're talking about the dot product of the magnetic field and the area vector, right, of the coil. So you see, and it is important also to be able to describe the direction of the current that is induced, okay, in the coil, okay, at the same time that there is an induced EMF or voltage. So imagine that there is an observer from the right end of the coil, right, looking into the coil. right? So he will be able to say that the induced current is directed, all right, such that the indicator or the needle of the galvanometer will be deflecting to the right. So if you're going to trace the direction of the induced current in the whole circuit of the coil, we say that the induced current is, we are talking about conventional current, that is. So the direction of the conventional current is that it is counterclockwise relative to an observer from the right end of the coil. But if the observer happens to be from the left end of the coil, then it will be the other way around. All right. So the description of the direction of the conventional current that is induced depends on the observer. All right. Relative to us, since we are looking at the figure, all right, like this, all right, we say also that the current, conventional current that is induced is counterclockwise. Finally, we now have the computations for our two main questions. In part A, determining the amount or magnitude of the induced EMF, or epsilon. So that is just equal to negative capital N multiplied by delta P sub B over T. That is, the induced EMF epsilon equals negative 455. That's the number of turns in the coil multiplied by delta P sub B over T, already calculated earlier, negative 2.21 times 10 to the negative 5 volts, or the magnitude of the induced EMF epsilon equals 1.01 raised to the negative 2 power volts. And in part B, determining the magnitude of the induced current, capital I, which is simply equal to the induced EMF epsilon divided by the given resistance in the coil, capital R, or that is 1.01 times 10 to the negative 2 volts divided by 14.5 ohms. So, our answer to question letter B, the induced current has a magnitude 6.97 times 10 to the negative 4 amperes. And that concludes our lesson for this topic. Until the next episode, mabuhay, mashallah. Thank you very much for your indulgence. Please don't forget to subscribe to my YouTube channel. Alhamdulillah.